lesson that ended just barely was cell respiration. And what this lesson did is it started us out with understanding what's happening in any combustion reaction. And it's just a burning candle in this case. And what we're seeing is that the burning candle goes out. Why does it go out? It goes out because the oxygen in the jar is consumed. And when the oxygen in the jar is consumed, there's nothing left for that reaction to keep happening, right? And the reason why that is because oxygen is the final electron acceptor for the combustion reaction, right? And the reason why it's such a explosive reaction is that we're releasing all of the energy at once. So if we're imagining high energy electrons in the paper, right? That's going all the way down to a low energy state on the oxygen. And so that change in the energy state results in heat being released all at once. If we contrast that to the fluorescent stars that we looked at in our chemistry lesson, the fluorescent star lets the energy out a little bit at a time, stepping down more like this as it moves down the energy levels. So our cells, we are going to do a combustion reaction, but we don't want that combustion reaction to be all at once, right? That would release all the energy of the food that we eat at once and we get burning, right? We'd have way too high of temperatures. So we want to do this, but we want to do it step by step and slowly release the energy. And this kind of gives us an idea of where the energy is coming from, right? It's coming from breaking bonds. When those bonds reform, energy gets released. We're also going to get high energy electrons out of this that we're going to use later in this process. We take those high energy electrons, we put them into a molecule called NADH. And every time we break subsequent bonds in our sugar molecule and reform new bonds, we get more high energy electrons. So that's kind of the idea behind this process. We're also just a moment. Sorry about that. Sorry about that. So what we're going to see is in the cell respiration process, right? As that energy gets released, as it drops down from one shell to the next, we're going to use that energy to cause active transport to occur. Instead of going from high concentration to low, we're going to force hydrogen ions to go from low concentration to high. And that builds up a gradient outside. And then those hydrogen ions will want to come back into the center, the matrix of the mitochondrion. And in order to do that, we're going to allow it to pass through, but it has to pass through this special channel protein. So facilitated diffusion here. So as it goes from high concentration to low, it's facilitated diffusion. And this special protein acts kind of like a turbine. It's going to allow the water to pass through. Not the water, sorry, the hydrogen ions to pass through. But as it passes through, it's going to turn the turbine. And there's this special protein, and that mechanical energy is going to be converted into chemical energy, into ATP, which we talked about last time, is that temporary storage that our cells need, molecule that our cells use to use the energy whenever they need it. So that is kind of the idea that Dr. Jensen talks about fully in the video. And so I don't want to go through everything in the video unless you have questions on it, because she does a great job explaining that and giving us a visual to go with it. But this is the general idea that we're doing, right? We're taking the energy from the bonds of the glucose molecule, and we're getting high energy electrons out of it. And those high energy electrons are used to generate ATP.